Okay, this is a tutorial on kinetics using some of our past work on iron oxidation as a good way to introduce the key concepts of chemical kinetics in aquatic systems. So the system that we're going to study is the oxidation So the system we're going to study is the oxidation of Fe2 plus, and that's an aqueous phase species, and that's iron in the +2 oxidation state going to Fe3 plus. So iron 3 plus is the thermodynamically stable form of iron in solution, and Fe2 plus is the reduced form of iron. This is an oxidation reaction. And that reduced form of iron is introduced into lakes, streams, aerosols, the atmosphere, and the oceans through a number of processes, but normally through either photochemistry that reduces the iron or anoxic waters, where water is flowing through sediments where there's been low oxygen concentration. If we were to start our experiment with 100 nanomolar of iron 2, and we were to then build an instrument to measure that iron concentration, I can have Fe2 plus on the y-axis, and we'll put our 100 right here. We'll start with 0 and 50, and then the x-axis is going to be time. And in these experiments, our time's going to go from 0 to about 10 minutes. And if we were to build an instrument to measure iron 2, we would add our iron and then start measuring its concentration. And what we would see is that the iron 2 concentration decreases with time in an exponential function. So now I'll go ahead and put a line through that data, and it would look something like that. So the change in iron 2 plus dt in this experiment is equal to K times the iron 2 plus concentration at any time. So if the K is what we call the rate constant, we'll put that in green. This is the concentration at T, and d iron 2 dt is the change in iron 2 concentration with time, and that is got a negative sign out in front because the iron concentration is decreasing. Now remember from calculus that dFE2 dt is the slope, so we'll just do that in purple, at any point along this curve. Okay, so this is a good, simple kinetics experiment or example, and it is an example of a first-order decay process. And the reason it's considered first order is that the iron concentration is raised to the 1. So we didn't include that exponent. It's implied if there's no exponent there. So this is a first-order decay process. You could fit this in Excel as an exponential function, but we often replot our data time as the ln of Fe2 plus. And when we do that, we get a straight set of data, and the slope, m, is equal to negative k. Now, why is that? That is because the integral of a first-order rate constant gives us an expression that says Fe, let me back up, I'm going to do this on a log scale. Make my cursor just a teeny bit smaller, there we go. Ln of Fe 2 plus at time t equals ln of Fe 2 plus at time 0 minus kt. So that is the integrated rate expression of a first order process, and you may have also seen it in this form, Fe 2 plus at time t equals Fe 2 plus at time 0 e to the minus kt. These two expressions, which I will now circle in blue, are exactly the same. One describes the exponential decrease in time when I'm plotting the iron concentration on a linear scale, and that's the bottom equation. And this is the integrated expression where I've now log transformed everything. So I take the natural log of the iron 2, I get ln of iron 2 is equal to ln of Fe2 at the subscript 0 means at time 0, and notice the e to the minus kt. If you take the natural log of that, that just becomes minus kt. So this is a very simple experiment where we, again to recap, we follow the decay of iron with respect to time. It follows what appears to be a simple exponential decay. Experimentally, that's exactly what we observe. The rate of change, which is the slope of that decay anywhere along that decay curve, is a first order process in terms of a rate constant, iron concentration raised to the first, and we often log transform that data so that we can take the slope to determine the rate constant. The rate constant in this case, K, has units of 1 over time. So notice dFe2 plus dt, that's going to have units of molar per unit time. So there's my K, there's my concentration, and so we now have 1 over time, molar, and my units are going to be molar per unit time. Okay, so the change in concentration over time in this case is a first order process. Okay, so everything I've just said is absolutely true. If you add iron 2 to water, it's going to rapidly get oxidized to iron 3. It's going to follow a first order decay. You can take the natural log, you can determine the slope to determine the rate constant K, and you can write that down. And the units in that K are going to be 1 over time. Beautiful. If you do the exact same experiment, in a lake or in a beaker, and you put in some iron 2, except in this case, you have no O2 gas. No dissolved oxygen. And you could have no dissolved oxygen because the bottom of your lake was anoxic, or you could have no oxygen because you bubbled your beaker with nitrogen from the lab and you basically sparged out all the oxygen. So there's no oxygen in here. If you do this experiment, nothing happens. Fe2 plus is stable. Okay, so again, my first experiment was right on. We add iron 2 to lake water or to a beaker in the lab, and it goes away in about 10 minutes. If you add it to anoxic solutions, it doesn't go away. So clearly, oxygen plays a role in the kinetics of iron oxidation. And yet our kinetics experiment says nothing about oxygen. This is often the case when we do kinetics experiments. We do them under a controlled set of conditions. We measure rate constants, but we aren't actually investigating the molecular basis for the reaction. What we're measuring is the net result of a whole series of reactions. And that's indeed the case for iron. In most environmental systems, iron decays in a first-order fashion. But the reason it decays in the first-order fashion has to do with a series of elementary kinetic steps. And now what we're going to do is try to discover what those steps are. All right, so the first thing that you can do is you can add in iron 2 plus, and you can put in 100 units. And I'm going to put in some oxygen, and I'm going to put in 100 units. And I'm going to allow this to react in a lab beaker. And I'm going to let it go to Fe3 plus. And if I allow that to react, I'm going to notice that I get 0 iron. I get, I'm going to start with 0. So this is start. And the byproduct of this is water. The other reactant here is water. And I've got plenty of water already in the beaker, so I'm not going to worry about the water concentration. That's the start. If I let this go for, say, an hour, so I'm not going to follow the kinetics, I'm just going to let the reaction go to completion, what I'm going to notice is I'm going to lose all of my iron 2, minus 100. But I'm only going to lose 25 units or moles of my oxygen. I'm going to produce 100, and then I'm not going to worry about the water. And so the final concentration of iron 2 is 0, but the final concentration of my O2 is 75. In other words, there is a chemical stoichiometry. Let's say that again. There's a chemical stoichiometry that is different than the kinetic mechanism. There is a chemical stoichiometry where I consume 4 irons per each molecule of oxygen. So my net reaction is 4 Fe2 plus O2 goes to 4 Fe3 plus 2H2O. Okay, and you might say, well, where'd those protons come from? The protons are coming from the buffered solution that we're going to work with. So we're going to put the 4 protons over here, 4H plus. And now everything is beautifully balanced. Well, what we discover experimentally is that the oxidation of iron, so let's switch to a different color here. The oxidation of iron is a function of H+, but that function is quite complicated, and we'll get to that in a minute. And we lose 4 irons per oxygen. So oxygen's clearly involved in the overall reaction. But again, this is a complex series of reactions, and we're going to sort of tease this out in our experiments. So the next thing we'll do to tease it out is we'll measure the kinetics as a function of the iron concentration. So measure K for Fe2 plus oxidation as a function of O2. So if we do that, this is O2 going this way. This is K. Well, maybe we'll back up a little bit. Let's think about how we do these experiments first. Time Fe2 plus. I'm going to do an experiment, and I'm going to do the green experiment, which is high O2. And then I'm going to do a orange experiment, which is medium O2. And then I'm going to do a blue experiment that's low O2. So I'll draw the low O2 experiment first because my pen's already that color. We're going to start with 100 here. 0, 0, 10. If we do our low O2 experiment, we observe something that looks sort of like that. The iron goes away, but it doesn't go away at a very fast rate. And then if we go to our medium experiment, they start at the same place. There's our medium experiment, and then we'll go to our green, which is our so the green goes away faster than our orange, which goes away faster than our blue. And these are classic experiments that you do in the lab. You set them up so that you can measure these kinetics as a function of oxygen concentration. So now I can go in and make my plot. Let's get that straight. This is O2 now on this axis. This is K, and it's the first order rate constant for the iron 2. And what we observe is that when the oxygen concentration is really low, the K is 0. No oxygen, no oxidation of iron. And then as we increase the oxygen, that rate constant goes up, and it goes up, and it goes up. And there is a linear relationship between the K and the oxygen. You double the oxygen, you double the rate. You triple the oxygen, you triple the rate. So now you say, okay, well, something's going on here. Oxygen's clearly involved in the iron oxidation. So we can now rewrite our rate expression, dFe2 plus dt is equal to K. And I'm going to put a subscript 2 here to differentiate it from the K I had at the top. I'm going to call that K2. Actually, I'll change my mind. I'll call that K1. And we can say that this K1 is a function of the Fe2 plus concentration and the oxygen concentration. Now you might say at this point, hey, what's going on here? You wrote it up here at the beginning. where it was only a function of iron, right? All the way up here, it's only a function of iron. And now we're writing it as a function of iron and oxygen. But notice I changed the value of K1, and my experiments tell me that the decay of iron is a function of the iron concentration, but it's also a function of the oxygen concentration. So when we did this originally, what I really did was K1 O2 Fe2 plus, and this term, if the oxygen was much higher than the iron concentration, the oxygen concentration in my experiments were a constant, and K1 is a constant, and K1 times oxygen equals K. So the change in iron concentration with 2 is a function of K times iron 2. This K is the first order, effective first order decay rate of iron. But we now know that the effective first order decay rate is actually a second order overall rate constant, which we'll call K1, times the oxygen concentration times the iron 2 concentration. There is also first order dependencies to both iron 2 and oxygen. How do I know it's first order? Because the plot of K versus oxygen was linear, therefore implying a first order dependence on oxygen. Okay, now that all makes sense in the context of my kinetics experiment, but it doesn't make sense in the context of my chemical stoichiometry. This reaction and the overall stoichiometry of iron and oxygen has a 4-to-1 ratio, not a 1-to-1 ratio. So clearly my chemical stoichiometry is not predictive of the reaction rate. So that's the next thing we need to resolve. How can I have kinetics which are first order with respect to oxygen, first order with respect to iron, and have a stoichiometry that's 4-to-1? Well, I'm going to stop there and pick up this video on the next iteration of this, so I have a chance to clear my throat and keep these videos a little bit shorter. Okay, back to kinetics. So we were talking about the fact that the change in iron concentration with respect to time was actually a overall second order process where we had K1 times the oxygen concentration to the first times the iron concentration to the first. And so now we should talk about what are the units for K1. The units for K1 are going to be 1 over molar time. And so again, our concentrations change in iron, Fe2 dt, is going to have units of molar per unit time. And since we now have molar squared oxygen times iron, we need to cancel one of those molar units. And so my unit on K1 is 1 over molar time. So how do we reconcile the fact that my observed rate is a first-order function of oxygen and a first-order function of iron, and yet the overall stoichiometry requires 4 irons to react with 1 oxygen? The way we resolve this is to recognize that iron oxidation doesn't occur in one, what we call unimolecular step, not one step, but actually occurs in a series of steps. And the first step, which we will call step 1, is Fe2 plus O2 goes to Fe3 plus O2 minus. O2 minus is a fairly unstable species. It's called superoxide, and it's oxygen with one extra electron. So you add an electron to O2, you get O2 minus. That electron came from the iron 2, and we can give it a rate constant. Let's see. Let's give it K1. Now, this is what we refer to as an elementary kinetic step or reaction. And it says that actually iron 2 collides with oxygen, and that collision occurs with a probability, K1, of forming iron 3 and O2. So since this is an elementary step, you can actually use the reactants in the elementary step to predict the rate. And I'll switch to blue. D Fe2 plus dt is equal to dO2 dt. They both go away at the same rate. Negative K1 O2 Fe 2 plus. Okay, so this explains the first order dependence on oxygen, the first order dependence on iron. They both go away, but again, we said, hey, there's 4 irons that go away per oxygen, and this equation clearly can't be the only story because I have a 1-to-1 stoichiometry here, not a 4-to-1. And the key is that I produce iron 3, but I also produce this species superoxide. And I said superoxide is reactive. And in fact, it is. So there's another reaction that occurs. O2 minus plus Fe2 plus goes to Fe3 plus O2 2 minus. Now, O2 2 minus doesn't really exist at a very high concentration in water around pH 7. That is the conjugate base of superoxide. So in fact, superoxide reacts with iron 2 to form iron 3 and superoxide, but O2 2 minus plus 2H plus goes super fast to form HOOH, which we call hydrogen peroxide. So now we have a way of thinking about how we might be able to consume multiple irons per oxygen. The first elementary step in our sequence produced a species superoxide. That superoxide can now react with another iron 2 to give me iron 3 and hydrogen peroxide. And so we will say that superoxide is an intermediate in this kinetic sequence. It is produced in one reaction and it is consumed in another. And if I can have one intermediate in this reaction, well, why not have a second intermediate? And this we will call K3. Now, K3 is not as fast as K2, but it's pretty fast. It happens on a time scale of seconds compared to the first reaction that occurs on a time scale of minutes, and the superoxide reaction happens on a time scale of microseconds. So this is my third elementary reaction for the oxidation of iron. Hydrogen peroxide plus iron 2 goes to iron 3, and two species, OH minus, so that's just the standard hydroxide ion, and OH dot, which is the hydroxyl radical. That is OH missing an electron. So look what I did. I broke the oxygen-oxygen bond in hydrogen peroxide. I gave one of those OH an electron, but I only had one electron to donate, and so the other OH stayed as OH dot. Which now leads me to my last elementary reaction. OH dot really wants an electron, so it reacts with another iron 2 with a rate constant K4 to go to Fe3 plus and OH minus. Well, you notice OH minus is kind of the same thing as water if you add a proton to it. And you'll notice that if you add up these four reactions, K1, the K2 reaction, the K3 reaction, the K4 reaction. Let's do a little iron accounting here. We'll do that in green. Okay, there's one iron. There's two irons. There's three irons. And there's four irons. Those four irons were oxidized from iron 2 to iron 3 by one oxygen. So these series of four sequential kinetic steps explain the overall stoichiometry that we observe when we react iron with oxygen. Four irons react with oxygen to produce four iron 3s. But it doesn't happen at once. It happens in a series of steps. And the series of steps, step 1, is controlled by the iron concentration and the oxygen concentration. And the last thing I need to tell you is that K1 is slower than K2, K3, and K4. And because K1 is much less than K2, K3, or K4, we say that the first step is rate limiting. And because it's limiting, it controls the speed at which, or the rate at which, iron is oxidized. The rate of iron oxidation is a function of both the iron and the oxygen concentration. It is a function of the rate K1, but the subsequent steps consume 3 more irons, and those 3 irons explain the overall stoichiometry of iron 2 going to iron 3 in the presence of oxygen.